All right, let's give it a go. Morning, everybody. It is an absolute pleasure to be with you here at NDC Sydney. My name's Phil Nash. I'm a developer advocate at a company called Sonar. Sonar does code quality tools that help you find and fix bugs and security issues as you write them, helping to avoid problems and write clean code. We have things like SonarLint, which is a free IDE plugin that you can use to check your code as you write. And then SonarCube or SonarCloud, which sit in your CI/CD pipeline to check on your code as you submit, as you commit and push. As I said, my name's Phil Nash. You can find me anywhere on the internet as Phil Nash normally, Twitter or whatever you want to call it, Mastodon, also still Blue Sky, LinkedIn, whatever. Or just go to philna.sh. It's an easy domain name to remember if you can remember my name at least. It helps me remember it, I guess. That's the important part. And today, this morning, I want to talk to you a bit about code and complexity. And I'll start with a bit of... I'm going to do this in like 3 parts. We're going to talk about what is complexity, how we kind of measure it, and then what we can do about it. And so in terms of part 1, what is complexity? Well, I kind of think that... I don't mean to flatter us all in the room, but our jobs are complex. We have to keep a whole bunch of stuff in our heads at any times in order to build the applications, build the sites, build whatever we're working on. The problems we're working on vary in complexity, but they are all of some sort of complexity. And we have to build code that kind of maps or abstracts onto actual real-life problems. And turning that kind of idea of a bunch of text the computer can understand into something that's going to solve a real-world problem is also inherently complex. It adds to that situation. And so whilst we deal with those complexities ourselves, we also, given the nature of code, have to deal with not adding extra complexities on top of it, accidental complexity, the kind of stuff that actually does make you confused about what you're actually building at the end of the day. And so effectively, our job becomes managing complexity. It becomes writing code that's going to solve problems in such a way that we don't end up writing overly complex things that eventually grind a project to a halt because we can no longer understand what we started with. Our job is managing that complexity, and when we do that successfully, then we have a good time. Our code base feels fresh, it feels new, and it feels like a joy to work in. When we don't do that, we don't want to work on it, we call it legacy, and then we ship it off to somebody else to work on. Or we try to, I don't know. And so I gave a talk over the course of 2023, sadly not here at NDC Sydney, because this is NDC Sydney 2023. I think we're just 2 months late. I gave a talk which is entitled "The Top 5 Issues in All Our JavaScript Projects," and this talk used some of the data from SonarCloud, which scans hundreds of millions of lines of JavaScript and TypeScript to kind of find out what issues came up most commonly in JavaScript projects. And these were the top 5. A bunch of them are, I think you could probably say, relatively easy to deal with, not too much of an issue. Using var instead of let or const is a problem, sure, because we have let or const and that can do a better job. But ultimately, it's not going to cause a project to come grinding to a halt. But the second most common issue that we found using static analysis was that the complexity of functions in JavaScript projects is too high. And that's what I want to kind of dig into today and see what we can do to handle that and recover that. And we're also going to kind of talk about what is too high as well. We'll see what this all matters by the end. But when we ask about what is too high, we actually have to start with a measurement in order to measure that complexity. And so that is part 2. How do we measure complexity? Has anybody got any ideas of kind of measuring, ways you'd measure complexity in your code base or something that you do? Maybe not Ben. Sure. Oh, sorry. How many of your colleagues hate you? Wow. If that's a metric that you're keeping up to date, I guess in like your own personal spreadsheet. David, were you going to say something? Cyclomatic complexity. That's a good one. I'll get to that in a second. Good. All right, cool. I just want to take like 2 example functions to kind of think about as we talk about measuring complexity. The first one is this function. It's a sum of prime numbers up to a maximum number. It's not for anything, it just does mathematical stuff. And when it does it, it uses a couple of for loops, it's got a couple of conditionals in there. How complex is this? It's understandable, it's not too many lines of code. It's not too bad. I just wanted to contrast that to a different function, definitely not mathematical, more about words. It still deals with numbers, but like this kind of function here is a get words function. If you put a number into it, you get out one or a couple or a few, or many or lots at the end of the day. And I sort of argue that like the first one with a couple of conditionals and a couple of loops and a bunch of stuff going on, and some unnecessary short names, but we'll deal with those later. That one I would argue is more complex than this. Now, David said cyclomatic complexity, which is great. It's almost like he'd seen these slides coming up. Cyclomatic complexity is a score that we can use to measure complexity. It was invented in 1976, so it's been around a while, longer than I have, incredibly. And cyclomatic complexity gives a function a score based on various things. It's a function. Basically based on how many different ways you can go through the function. And so you get a point for being a function, and then you get points for other things like breaking in loops or conditionals. And so our sum of primes function here scores 1 for being a function. Woo, up the top. It scores 1 for being a function. It scores 1 for this first for loop. It scores 1 for the second for loop. It scores 1 for this conditional. And then we got one more conditional, so we get a score of 5. And there are 5 different ways. You'd have to write 5 tests to cover all of this. But it turns out that the getWords function also scores 1 for being a function and then 4 for each case in its switch, and is also deemed as complex by cyclomatic complexity as our sum of primes number. And so cyclomatic complexity is useful. It is useful for knowing things like how many paths you have to go through a function, how many tests you'd have to write to cover it. I'm not in any way saying that this is not a useful measure of something, but complexity, or at least how easy it is to understand a function, how easy it is that you might be able to continue to work on it, it's maybe not quite so much. It doesn't quite fit that mold. And so how do we measure that understandability? How do we measure maintainability in a code base? I want to posit that cognitive complexity is a pretty good measure of this. Cognitive complexity was come up with in 2016 by some of the people at Sona, where I work. I've only been there for just over a year, so not score. I'm not trying to big up my own work here, but just the work of my wonderful colleagues who were looking to find a better way than cyclomatic complexity to measure this. And cognitive complexity still gives you a score for a function. So it's still a number at the end. It's still trying to quantify that. But it does so in a slightly different way. Instead of just incrementing for those breaks in flow, which it does do, it also keeps the idea of a nesting score in the back of its mind. And so each time you nest, we increase a nesting score by 1. And then each time we break in flow, it adds both 1 plus the nesting score at the moment. And so you start with a nesting score of 0, and then keep adding as you come in and out. And so if we were to apply that to our sum of primes function, we no longer have to score it for being a function, like everything's a function. And the idea of a function with 0 cognitive complexity is the idea that we get a function that just has each line that runs happily after each other line, and you can just read it like a story from beginning to end. And I agree, that has pretty much 0 complexity, at least in terms of what you're reading at that time. But in this one, we score 1 for our first for loop. We score, so then in the back of our minds, we increment nesting to 1 as well. We get to our second for loop, and so we score 2 for that, which is the 1 for nesting plus 1 for being a loop. Our conditional in the middle is nested twice, so it scores 3, 2 for nesting, 1 for being conditional. Then we drop out of the conditional, we drop out of one of the loops and into another conditional, so that one's scoring 2, because the nesting is now just back down to 1. The cognitive complexity score of sum of primes here is now 8, as opposed to the 5 we had before. But our getWords function is now 1, because we have a big switch statement. And that makes sense to me. It feels a bit more right. Like a switch only deals with that one thing at the top, and we're comparing it a bunch of times. If this was indeed a set of if-else statements, it would score 1 for each of those ifs in there, because an if-else or an if statement suggests that it could be a different thing under test each time. Whereas the switch, we're only ever testing that one thing. And so I feel like cognitive complexity works a bit better And I kind of think about it as like your brain stack of how you're thinking about things. As I go through a function like that sum of primes, I know that as I hit that first for loop, I'm like, okay, now we're looping through some things, and I've got to consider that we are inside a thing and dealing with one part of the loop. And then we get inside that, and we're dealing not with one, but with two parts of the loop, because we actually have two looping variables that we're using at any time. And then we get to a conditional in that. We just keep kind of adding things onto the stack. And then as you get through things, you then pop things back off again and go, okay, this is a bit simpler. We're just in that first loop, but then we've got another conditional to add, and I'm like, it's a bit more complex than simply running through a switch statement, for example. And eventually we pop everything off the brain stack, we finish the function, and hopefully we worked out what was going on in the middle of that. But it's quite a lot of kind of inputs and outputs to the brain that make it just more complex to keep everything in your head and understand what the function's doing. I will also understand that a complexity of 8 and a function that can fit on a slide is probably not complex enough to worry about for anybody in this room, but we are worried about maybe things more complex than that. So let's get on to conquering that complexity. What are we going to do when we find we have complex functions to deal with? Let's see, the first problem is that we need to find that we have complex functions to work with. Understanding where the complexity is our first thing. We have this score, we have this way of scoring things. We need to sort of automate and understand where that complexity lies in our applications. I'll show you a quick demo. I have an unnecessarily complex function to look at. Oops, that's my slides. That's exciting. Give me 1 second. It stopped working, so that's exciting to just to let you all know that we're going to find this thing soon. So this is a little project of mine called Reveal Confetti. It shows confetti on slide decks. You might see some of it later. And it's currently not complaining at me. Cool. There we go. All right, that's fine. So it's Reveal Confetti. It runs on the end of a slide transition. So we have this function on slide transition end, which I can tell you scores 16 in terms of cognitive complexity, which should trigger an underlining on this particular page, and it's not. But I am still seeing that we have the locations of what's going on here. So I'm using Sonolint in my editor here just to show this off. And what it's going to do is show me like where all the complexity from this function is. And so like we start with a big if around the outside, which is scoring 1 for us. You can see that just there. And then inside we have a ternary, which is scoring 1 for being a ternary, 1 for a conditional, and 1 for being nested. And then we have another one, which is also nested at the same level, same as about this if. Eventually we get down to 3s and 4s. Yeah, so inside 7 here is a +3. It's a ternary that's inside 2 nested conditionals. And this is, it's just a little bit hard to read. There's another nested conditional there. It's cost 4 just to make sure that this thing hasn't finished yet. So that's kind of nested in this particular case inside of a internal function as well, which the function itself doesn't incur any score for nesting, but running things from within it does. And that's just a big settings block. But this function, you know, it's almost 90 lines of code, comes out as a score of 16, and Sonolint here is suggesting that I could do some stuff to fix it up, and I appreciate that. Thank you, Sonolint. I will go and fix it up. We'll fix it up with some ideas in a bit. The second thing after finding out where your complexity is in your project is to not do anything about it. So you want to breathe a sigh of relief. You're not currently under any stress for handling this right now. Because it turns out that if you find out that you have a complex function somewhere, but it's doing its job and it's doing it fine, like there's nothing wrong with it, it doesn't need anything added or taken away or fixed with it, we don't have to worry about its complexity. The complexity of code only really matters to us if you need to change it, if you need to load that code into your head and understand what it's doing. If a function is working as expected and has a complexity of 2000, I don't care, as long as I don't have to change it. If it turns out that any of you have functions that have complexity of 2000, I need you to tell me about it, because I would really like to see that. I have found in open source projects complexity of upwards of 100, 120, but nothing in the 4 figures yet. So actually, if it's over 1,000, I'd love to know. I really would. But again, if it works, if you know it works, like you kind of have to know it works as well. But if it works, then you don't need to touch it. And if you're not adding features to that part of the code base, you also do not need to touch it. Complexity is only an issue if you need to change that complex code. And so this kind of brings me on to then step 3. This is where you might have to change something. And this is kind of an idea that we espouse at Sonar, which is that we want you to eventually work towards clean code, a clean code state where nothing is complex and a whole bunch of other issues are also solved. And we take that idea of cleaning as you code. If you have to change a function, if it turns out you need to fix something, add a feature, take something away, whatever it is, and you find that you've got an overly complex thing or some other errors with it, we kind of encourage that you clean that up as you are coding. Fix it, or fix it first, then make the change, and possibly even refactor again afterwards in order to make sure that you are leaving that code base in a better state than it was before. If you continually do this, if you always work to improve upon bits of code that you're working on, then ultimately over time your code base is going to become a much better place to work in. And so we say clean as you code. And I reckon the way to do this is to refactor first. Like you come across, you've got to add a feature to your reveal confetti plugin. We need to have more confetti. We'll see lots of confetti, it's fine. I'd always say to like refactor first. Before you have to make a change to the product, make it to a function, you should make it easier to make that change in the first place. Doing that refactoring first will be easier. You've not added extra code to it at that point, but it also makes it easier to make that change ultimately as well. Refactoring first also means you're improving how the code works without changing what the code does. And that's really sort of the most important point here about refactoring in general. When you are changing how the code works without changing what it does, you should absolutely do so without editing anything. But we do need to have things in place to make sure that we don't change what the code does. And I hope that you're all a fan of tests that cover your code and give you that confidence in what it does. Tests are the absolute kind of most important thing when you're coming to refactor a thing, because if you change some code and you cannot tell that it is not doing, or do it, if you have no way to verify that it doesn't do the same thing that it did previously, you cannot know that you just refactored something. All you can know is that you changed some code. Tests absolutely have to cover that to give you that confidence that you haven't broken anything. And more importantly, tests should also ensure that they test what a function does and not how it does it as well. So in refactoring, we're changing what it does and not how it does it. Sorry, in refactoring, we're changing how it does it, not what it does. The tests must ensure that they test what it does and not how it does it. If your tests are in any way tied to the implementation on the inside and you change that implementation, you're going to break the tests. And that's a bad spot to be in. Now, you think you've changed the code and refactored it without breaking anything, but the tests have a different opinion about that. And that's not the best place to be in. So yeah, do not kind of rely on those interior details to a piece of code in order to test it. Otherwise, refactoring is going to break those tests. And so if you don't have tests covering your code, step 1 of refactoring is absolutely to come up with some tests that are going to cover this, going to verify that your piece of code currently does this, and after we've changed it, continues to do that. And the important thing here also is if we are refactoring before we are here to fix a bug, this refactor shouldn't fix the bug. That would be changing how the code does something. The refactoring is only going to, that would change what it does. I'll start that again. If you are changing something and you're trying to fix something, refactoring should not include that fix. We are changing how the function does something and not what it does. If currently what it does is wrong, in order to refactor it, we have to maintain that it is wrong at the end of the refactoring as well, and then we can fix it. Those are 2 separate processes. test must cover that existing behavior, and it must cover the existing behavior even if that behavior is wrong, so that we know that we haven't changed anything else about our system when we finish the refactoring. And once you finish the refactoring, that is the point where you can fix the issue separately. It should be easier to do so at that point. It's easy to think about and keep that code base in your mind, but ensure that your refactoring is not encroaching on feature adding or fixing. So yeah, then we get to the point where we refactor. I've got some ideas as to how we can refactor with the idea of cognitive complexity in mind. There are many, many refactorings available and ways to refactor. And I highly recommend, Martin Fowler's book on refactoring, also Sandy Metz, Katrina Owen, 99 Bottles of OOP, both excellent books on ways to approach refactoring and things like this. I just want to think about it in terms of just that cognitive complexity and how we're going to keep less stuff, I guess, on the brain stack and reduce our complexity so we can, over time, make it easier to deal with our code base. And so because cognitive complexity itself punishes nesting effectively, the best thing to do to reduce your complexity is indeed to reduce that nesting. And there's kind of 4 different techniques here that I would suggest you'd aim for. First up is inverting the condition and early exiting if you can. Inverting conditions and early exiting. Structural collapse is second. Extracting helper methods, and then some other language features that I'll cover a couple of, for JavaScript at least, at the end. So inverting conditions and early exits. This really comes to, I genuinely wrote my reveal confetti to be written, but I didn't actually think about it. It turned out I put a big if statement around the whole thing to say at the slide transition end, the sound. Hello. Are we good? Okay, I'm back. I can hear it again. I'll stop moving. I had a big if statement around the body of this function that just says, if there's confetti in a data attribute on the current slide, then let's go for it. Let's do some stuff. And this, of course, starts as nesting stuff. It puts I have to consider whether confetti is on the slide onto the brain stack. I have to then think about the rest of the things. But if you invert that condition, if you get out of that early, if there's no confetti, then we don't have to think about anything else. We can early return. And I told you it was coming. We can early return, and the function doesn't have to worry about anything else. And in terms of that kind of brain stack of things, all you have to know is that everything else from this point onwards is what you were intending to do anyway, and you just dropped out early because you didn't have to worry about the other thing. It just pops it off the brain stack, and it makes me happier when I think about it that way. Structural collapse, on the other hand, this is sort of a more made-up example and isn't in the current code. But structural collapse is where you find that you've got like kind of 2 conditionals next to each other that nested within each other, but don't actually have to be. It's surprising how often this kind of comes up. And in this particular example, this is 2 things that are going to deny us putting confetti on screen. One, in this case, this is 2 things that allow us to put confetti on screen. That is, there's confetti on the data attribute, and the current window has a media query that says, nobody has said, don't worry, stop animations. No preference for prefers reduced motions. It's a whole set of negatives. Thank you, CSS, for that. But it basically says we don't want animation. We're okay with animation. And so if confetti is on the slide and the data set, okay, then we can throw confetti. But we don't need to nest that. We can just put it all into one thing and throw confetti. Both confetti is on the slide and animation is allowed. That is reduced, and everything incur an issue in between or one less. And it pops off the brain stack. That's one less thing to think about. We don't have to worry why we're nested so deep. We've just got through our condition easily. Third one is to extract helper methods. part of my code, I do find that I reach into the data stuff and turn it into, in this case, an integer with the default fallback. This, in the first version of the code that I wrote, used a ternary each time to check that the thing existed in the data set. And if it does, it passes it as an integer. And if it doesn't, it returns the default. And so we get 200 particle count of confetti, and it can take 0 seconds. Those are kind of the defaults. But this is now duplicated code. We're incurring a score for each of these conditionals, and not just one for each of them, but 1 plus whatever nesting they're in each time we hit them. And it's just duplication. It's stuff that we can extract. And so if we extract it to a function that is named after what it does, in this case, it returns an integer data attribute or a default, then we can use that in our code. And when we are reading the code, it tells us what it's doing rather than having to mentally parse a ternary conditional in this case. And it's going to dry up that code, right? It's stopping us repeating things. But it also, as you're reading that, hopefully it does make more sense than having to read a ternary. I dislike ternaries anyway. But this one runs over 3 lines. Why have I even ternaried that? It's very annoying. So extracting a helper method, whatever you've got there, if you are repeating stuff, or even if it is just a sort of complex bit of code that you can actually name something which makes a lot more sense than trying to read the code itself, then you are helping yourself to read it. And then secondly, actually, because you are extracting a helper method, you can then test that method independently as well. We can now be happy that these methods are working independently of everything else that is going on, giving us, again, greater confidence in the overall ability. In terms of our refactoring, we're still only worried about not breaking the tests whilst we change stuff. But if we wanted to, add further tests to be certain about these other sort of units of code, then we can do this. You can't add. You can add more tests to your main. Sorry about this. Don't know which part of the microphone is to me. Anyway, once we extract that helper method, once we have a good name for it, once we've named the concept of what we're dealing with in this thing that's worthy of being its own method, we can understand what it's supposed to do without knowing the details of the code. And again, score less on cognitive complexity, pop it off the brain stack. And finally, there's just some of the newer features of JavaScript that help us do this in other code like this. If you have nested objects that you need a property that's somewhere deep inside of it, you probably find yourself a few years ago, checking that the first property exists and then moving on to the second property. And if you have to go deeper, then you get longer and longer chains of make sure this exists and then this exists and then this exists before we finally get the value that we want. But instead, we now have optional chaining, which just removes that extra and. It removes sort of conditionals that we have to consider and is just an understandable line of code now. And secondly, something like if we set up a defaults object, do something with it in the meantime, and then later we want to set the colors on the defaults, but only if it's not already been set by something else, then we would have to check that if the default colors is already undefined or null. And if it is, then we can set it to something. And if it's not, then we just carry on. But this is adding conditionals. It's adding stuff to think about. And JavaScript even more recently added our nullish coalescing, you know what I mean, nullish assignment. So if default colors in this case is null or undefined, it will get assigned. If it's anything else, it will not. We've dropped out a conditional. We've made things a lot happier there. We've popped it off the brain stack. I just feel like the less things I have on that stack, the happier I am. And those things all allow us to help. Ooh, bonus rant. Yeah. I mentioned ternaries. So, I'm a big fan of Prettier. It's a wonderful formatter, helps us make our code look a lot better. One of our other tenets of clean code that we try to talk about at Sonar is consistency, and formatting is absolutely key to consistency. So formatting is something you absolutely should have in all your code bases. It stops bike shedding about things. It stops arguing about what things should look like. Just let a formatter do it, and it's great. Certainly, Prettier has been considering nested ternaries. In fact, it's been considering them for quite a long time, since it stopped indenting nested ternaries after previously it was indenting them, then it stopped. Then there's a GitHub thread of 300 comments where they're like, they should be nested, they shouldn't be, they should look like this, and there's no agreement in the internet about what nested ternaries should look like. So Prettier have put out an experimental format for nested ternaries that ends up looking a bit like this. This is their example. And on some lines, when it's short enough, things can happen on the same line. If things are a bit longer or whatever, it will happen over more indented lines. And I don't care, because we should be nesting ternaries. This is a bad idea in general. I don't like reading this because we've got an animal name. We have to, again, this is just dealing with nesting it's adding things to the brain stack. We've got a pet that can bark, and if it is scary, then it's a wolf, although why is that a pet? I'm concerned about that, but it's just the example code. So we've got a pet that can bark, and then we check if it's scary, and then it's a wolf, and if not, it's a dog, and we pull back out of that to another else. And in my mind, I'm definitely changing colons. Have to, and then we're like, okay, now it can meow, and then it's a cat, and then we've got another else, it's probably a bunny. I hate it. It's nested, it's horrible. It's hard to opinion. Other people have different opinions about it, but arguably, due to its nesting, it's more complex. And we can use a couple of the things I've just talked about: early returning, inverting conditionals, and even extracting helper functions to do this better. That ternary, whilst shorter, more line, I guess shorter than this function, is much less readable. This animal name function takes a pet, and if the pet can bark and is scary, it's a wolf. That's easy to read. And if it just can bark, it's a dog, and if it can meow, it's a cat, and the result is maybe a bunny. We're returning out of this early, so we don't have to keep thinking about stuff. If we know we've got a barking, scary pet, we can stop thinking about it after the first line, and so can the code. But even better, we've extracted this as a helper function, which means we can test this, and we can write down tests as to which can verify what's going on inside what was previously an honestly ugly nested ternary, and now is something that we can reason against in our test suite. You could just extract the ternary to a function and test that, but I think this has made things better overall. I wrote a whole article about this because it's not just a bonus rant. I put it on the internet and then on Reddit, and I'm sure you imagine where that went. But that's it. So that's kind of what I wanted to cover today. I've talked a bit about what complexity is. Our jobs are complex, code is complex, and our jobs is to manage that complexity. If we manage it well, then the only complexity that we will find in our projects is that of the domain we're actually modeling, and not of additional complexity that we add through our own use of code. Measuring complexity, there are many ways to do so. I've heard of just using the number of lines function to measure the complexity of it, and that's, it's also a heuristic of sorts. Cyclomatic complexity is quite useful, particularly if you want to use it to know how many tests you need to cover everything. And cognitive complexity is certainly one that resonates with me, I hope it does with you, as to proving that something is hard to understand. And then when we come to conquering this complexity, we look to refactor things. First, we must have tests to cover that code. Again, a good reason to check on that cyclomatic complexity number to make sure we do indeed have enough tests that cover this. We should have those tests to cover it. And if we don't, first job is to write them and to cover the behavior that happens already. We should then refactor without changing that behavior, followed by doing whatever we need to do to the function to fix, add a feature, or even remove features. And ultimately, we can then, once we've tested and made that a solution, reconsider once again, refactor it again, if again you have added more complexity as part of this kind of feature add. And at the end of all of that process, refactoring, changing, final refactor, you can commit with the knowledge that the code base is now in a better state, not just because you did the job you were asked to, but because the code is much better as a result of it. And that's what we want. I think ever improving code bases are the way that we're going to be ever happier as developers. So I have some tools that are going to help you with this. Obviously, I will tell you that Sonar Cloud, SonarQube, and SonarLint are going to help with this. Sonar Cloud will do so as part of your CI/CD pipeline. It is free for open source projects. So if you want to check the quality of your code for an open source project, go check out Sonar Cloud right now. It's easy and free to sign up for. SonarQube you have to run yourself, and there is a free community edition for that too. SonarLint lives inside your IDE, also free, and can tell you about cognitive complexity as you are writing the code. And I think that is absolutely the best place to be doing this. You don't want to check in and several hours later hear that you wrote a way too complex function. It is much easier to fix things as you're working on them than it is to reload everything into your brain and get back into that same state of mind. Of course, if you already have ESLint in a JavaScript project, ESLint doesn't currently have a rule for cognitive complexity, but the Sonar JavaScript team also maintains the ESLint plugin Sonar.js, which has a bunch of rules in it, but does include cognitive complexity. And so you can just enable that, or check out the other rules as well, just to see what you might be missing out on. I will share these slides. Those are all links to places, but also Google. I do have some other links. There was a whole paper released on cognitive complexity back in, I think actually turned out to be released in 2017. It's very readable. It's actually really great. I've read it a surprising number of times at this point, and I don't tend to read computer science papers at all. And it's great. So check out that paper. It does go into a bit more detail on how things work, including some other measurements like if you're using logical operators, it doesn't incur extra points unless you're switching operators somewhere halfway between a thing. And I didn't want to get into that today because I didn't have any examples of switching Boolean operators. Go read my blog post on stop nesting ternaries and share it with everybody you know, because I never want to see one again. I don't care how nicely it's formatted. I never want to see it again. And finally, if you also want confetti on your slides and you use Reveal.js, you can go get that on GitHub as well. And you can make it do this. So that's it. Let's get out there. Let's beat complexity in our functions. Thank you so much for joining me this morning. Again, my name's Phil Nash. I'm a developer advocate at Sonar. I'm around for the rest of the week, so I'd be delighted to meet and chat with you about any of this, or hit me up online if you need that. Otherwise, thank you so much. And I guess we've got time for questions if anybody wants to shout out. I don't know if we have a microphone for questions, but there's some discussion at the back. I might borrow it myself, make sure I can still be heard. We do have a microphone for questions. Yeah, if anybody has a question, throw your hands up. Or if you just want to storm straight to lunch, that's also fine. I think it's lunch. Yeah.
Thanks, Phil. That was really good. A lot of good points there. But ultimately, I mean, you're moving the complexity out of your method, but then you're bringing your complexity into how methods work with each other. Does Sonar Cloud give you some tools to reduce complexities of like long classes or things like that with too many methods?
So Sonar Cloud or Sonar things in general tend to point out how things go wrong and suggest ways in which to fix them. And fixing complexity by kind of extracting things to other places is just sort of part of that suggestion. Now, I agree. The issue here is that you are anything that you do in code incurs some sort of cost, right? Nothing is free when we're changing things, changing how they work. And so I think the important thing is that whilst you're considering how best to refactor something like this, yes, you have to deal with talking back and forth to functions instead of just having everything in line. I agree with that. And that does make it complex in sort of a different, on a different axis. However, I think the benefits you can gain from, say, extracting helper functions, potentially testing them independently, and the way that you name them for the things that they do, I think that overrides the difficulty of having duplicated code or overly complex code inside one thing that you have to read through. If as you are debugging a function, you can pinpoint down to this one method call in the middle, rather than having to find it in the mess of conditionals and loops that an overly complex function would be, then you can pin down where you actually need to fix it as well. And so, it's not moving code around doesn't fix everything, but I believe that sort of that naming and understanding of both the abstractions and the things that you're dealing with inside of that code ultimately means that the cost is outweighed by the benefits. Does that make sense? Do we have tools to fix that? No, I don't think so. But we do certainly have. We're gonna. Sona is definitely going to suggest that you're not making functions with 18 different arguments and things like that. If as some way to make it so, writing poor abstractions that don't help you out in this kind of thing will be kind of called out in other rules and other ways. So there is stuff like that, but in terms of the overall shape and size of things, we're working on more architectural stuff, but right now it's more at the functional level. Yeah, got one at the back there. Microphone's coming to you.
Yeah, small question. Does the cognitive complexity function in Sonalint have support for all languages that Sonalint has? So,
yes.
like C# and Java and...
They do it for those major...
Okay.
I couldn't promise you that it definitely does it for PLL, because I've never seen a line. If you want to check that out, check rules.sonasource.com for the languages you're looking for it in, and you should be able to find it in that language. But yeah, it does cover for most, if not all. I can't think of one that it wouldn't do, but I also, I haven't checked every single language myself.
Yeah, no, that's all good. All right, thanks.
We got one down the front.
This might be a silly question, but thinking about function complexity, like big O notation, if you're dealing with recursive functions, I'm just thinking, will it flag, an O of n or something that's more efficient, like log of n? How would it flag those things?
So cognitive complexity doesn't concern itself with time or memory complexity in that respect. It certainly does still count things, but like the way I described it, and as I pointed out in the kind of code, when you have a nested function, for example, it doesn't count the function being nested itself as an additional score, but anything that is happening within there scores on that. But no, it is not over complex things in terms of time or space. But on the other hand, sometimes you can't write a piece of code without that either. And the things that we try and check for are sort of as verifiable, and we aim for precision, for accuracy in terms of things. That'd be really annoying if you had to write an order n cubed thing because you had to, and it was just being like, this is going to... you don't know what I'm trying to do here. So we don't deal with that kind of stuff. But it's much more on the... leans on the side of trying to make the code base better for you to work in, as opposed to be correct or not take forever.
Sometimes you can't avoid.
Exactly. Yeah.
Cool. Thank you.
Yeah. No worries. All right. I think that is it. Well, thank you so much again for joining us. Again, I'm going to be around for the rest of the week. Apparently, I'm running a karaoke party tomorrow night. Woo! I'll see you there.